Very much. Thanks to the organizers for the invitation, and thanks for the very nice talks yesterday. Last time I gave this talk, Christian fell asleep. I hope to do a better job. It's never connected to this side.
We can have one of the cameras on Christian.
No pressure. Yeah, so this is work that started a while ago with Chang Zhuang, who was a PhD student with me, and that we've pursued with Mauro more recently. So I will go first through the overview of the take-home message. Okay, so basically we talk about novel, between quotes, sequential Monte Carlo samples, with a focus on sequential Monte Carlo samplers that are going to exploit deterministic flows that are solutions of ODEs and their discretizations. And as we shall see, so we already know that this can be useful. So Hamilton's equations have been thoroughly exploited in this kind of context in order to move samples around the space and explore the support of the target distribution. But one can also, as illustrated in Mauro's poster yesterday, one can also use this kind of ideas to sample or approximate distributions that are supported by a manifold. And in fact, more generally, and I will try to illustrate this from my example. They also offer the possibility to exploit some of the geometrical properties of target distributions, right? And one of the key aims that we had in mind when developing this is to try to avoid computational waste as much as possible. And you'll see what I mean. And the simulation suggests some very good performance, but there's absolutely no real theory to explain everything. We've got bits here and there, but nothing really coherent. Okay, and we haven't explored these techniques in the state-space models context at all. Right. So I will just introduce not SMC samplers, but the notation that I'm going to use throughout. So here we are going to be interested in sampling from mu, which is defined on Z. And basically, in order to achieve this in SMC, we introduce a sequence of intermediate distributions. So there are capital P+1 of them. So the mu n's. And of course, the final distribution should be the distribution of interest. Mu naught is a simple to sample from distribution. And the idea is that the mu n's interpolate mu naught and mu p. And the main idea when implementing this algorithm is to propagate a cloud of samples that are going to represent these distributions. And I can skip this example for this audience. So there are key ingredients when designing this type of algorithm. So first, the sequence of distribution that you're going to use to interpolate the distributions of interest. So you've got the mutation kernel, which is going to be the way you move samples around. So I denote them MN here. And with those kernels, you're going to sample mutated particles, which may not be distributed according to the Dex distribution of interest. So in order to compensate, to take into account the fact that you're not necessarily sampling from mu n here, when you consider the Zn tildes, basically you introduce an importance weight. And despite the notation, this is the standard kind of importance weight that we are all familiar with. And then there's a selection step where basically we sample the next generation of samples according to the distribution defined that is proportional to the weight. So nothing very new here. So just one thing, and we all know that we need a backward kernel in order to define importance sampling on the joint space. And we know that a particular choice of of the backward kernel is going to lead to a simplification. And in fact, we are near optimality in a certain sense. And in a way, that's the choice that I'm going to make throughout the talk. But of course, we could be more general. So in some cases, the importance weight for certain choices of LNs, basically, we are going to get weights that simplify to this simple and familiar expression of the importance weights. One thing that is important is that typically to get this kind of results, what you require is Mn to be mu n minus 1 invariant, okay? And this somewhat explains the popularity of Markov chain Monte Carlos when implementing this kind of SMC methods, because they allow you to somehow get close to optimality, simplify the importance weight at the same time. But the price to pay is that basically you've got to use an MCMC in many scenarios, okay? It's not a theorem, it's just what happens in many scenarios. So here is the algorithm. I don't need to stress on this. And here on this picture, which has nothing to do with SMC, okay? It's actually a particle filter, but the idea is the same. It's just to illustrate the idea that from one generation to the other, so we go from one distribution to the mu n minus 1 to mu n, you see that we mutate the particles and we only generate one particle per particle, right? And then there's a selection mechanism. So that's the important. So when you go from one distribution to the other, we just create a new particle, typically, typical implementation, and then there's a selection step. Right, so now I'm going to switch to the integrator part of the talk. Okay, so ODE, flows, and same. So in what follows, everything that I'm going to talk about can be thought of in this way. That is, we are going to think of an ODE that is of this form. So Z is indeed the thing I'm trying to sample from. B is a field, and we are going to consider some discretizations of this kind of the solutions of this kind of ODE, and that's the notation I'm going to use for the integrators. Right. So, for example, a familiar example, or if you're not familiar with Hamilton's equation, here they are. Okay. So, in this scenario, we are interested in sampling from pi of x, right? But we extend the space we are going to sample from by introducing a so-called velocity or momentum, right? V, and so I call the pair XV Z. And basically, the motivation for HMC is to say, actually, can I define a mapping which, if I give you a sample from mu, then the mapping phi of Z naught defines another random variable which is also distributed according to mu. So that's the basic idea. And it turns out that the solutions to of Hamilton's equation ensure that indeed this property is satisfied. So in particular, what happens is that basically they are designed in such a way that the density along the solution of the ODE, provided it exists, etc., basically the density doesn't change. And this is the main idea that is behind many of these HMCs or Hamilton Monte Carlo algorithm. So this is what Hamilton's equations look like. So U here is minus the log density, right? And this is what the continuous time Hamilton equation look like. And if you can solve these equations, then basically you preserve the density. And indeed, if I give you a sample from U and you apply the flow to that sample, basically the resulting quantities that you're computing are also distributed according to mu and hence pi. Okay, and here is a picture from a nice paper. So there's the notation is a bit different. So this is X, this is V. And basically here the problem is one-dimensional. X is one-dimensional, V as well. So that defines the joint distribution mu. And you see that this is what an ideal algorithm would do. You just follow the contours of that distribution. And of course, you're only interested in what's going on here on the X axis. Okay. So in reality, one has to discretize. Okay, the solution to it's very rarely the case that one has access to the flow of DODE. So one typically, instead of solving exactly Hamilton's equation, one discretizes. Okay, and with discretization comes errors. Okay, that is, we sort of follow in good scenarios the contours, but not exactly. Okay, and this is why one typically uses a metropolis Hastings accept reject algorithm or important sampling, for that matter, in order to correct for the error. But at least the idea is to use Newton's equation does in order to somehow move the samples around the state space in an efficient manner, right? So here is the leapfrog integrator. So you don't need to learn the formulae. What is important is that they are very easy to evaluate, provided you've got access to the gradient of the energy, right? And in general, in this scenario, we do not preserve equality, okay, of these quantities, and but there are some nice properties. So basically, we are not too far off from the very general conditions. So this epsilon is the epsilon from the discretization. And also, there's no need for a Jacobian. Okay, so it's a transformation, but there's no need to compute a. Okay, and this is what the hybrid Monte Carlo algorithm looks like. So at iteration I, you may or may not sample your velocity, basically from the distribution. What you do is that I've given you the sample from the previous iteration. You replace V with the refreshed velocity. You compute this acceptance ratio, and you see that here, basically what we are using is the endpoint of the trajectory of the Hamilton's integrator over a horizon of t, and then we accept and reject using the standard thing. And of course, when you compute psi t, basically you compute psi 1, psi 2, up to psi t. Okay, and here you see that we are not using those values, right? So that's one hint at what's to come. So now back to SMC after the detour via MCMC methods. In the SMC methods, we are going to use, for example, this type of mutation kernel. So we are going to use Hamilton's equation again with this kind of integrator, okay, and this kind of acceptance ratio. And of course, again, basically, in order to be able to compute this, you need to compute all these states, right? But we are not using the intermediate state, which may provide us with some information about the target distribution, right? And that's really a pity, especially as when considering the leapfrog integrator, you see what you need to do is that for each intermediate step, you're required to compute the gradient of the energy, right? And very often, again, that's not a mathematical statement, but that's a practical statement. In many scenarios, basically, some of the expensive quantities that are required to evaluate the gradient are similar to the expensive quantities that are required to compute the energy itself, right? So that's often the case. So here is a toy example to show you what I mean. So if UN is just a quadratic form, then the gradient is 2 times this product. So of course, if you compute this thing, basically, in order to get the energy, you just need to multiply 2 vectors. Okay, so it is very important not to use all the intermediate steps, especially as you've devoted quite a bit of effort to computing those gradients. Okay, and of course, a natural idea is to say, well, if you've got access to this and it's then cheap to evaluate this, then I may correct for the error using important sampling, right? So that's the remark along the way. So one can think about how to do this in the context of MCMC. I'm going to focus primarily here on what happens in SMC. But now I'm going to make another detour, okay, especially because Mauro talked quite a bit about many things yesterday. So I'm going to talk about something slightly different to show you what I mean by exploiting the geometric properties of the target. So I'm using here an old friend, so the banana shape distribution, which is defined like this. And you see there's a non-linearity on the second component that you inject in a normal probability density. And of course, when we sample from, so here, let's consider the scenario where the dimension is d equals 2. So we only consider the first two components, okay? And these are the contours of the banana distribution, okay? Of course, when we update x1 and x2, what we'd like to do is to exploit the dependent structure of the target distribution. So if we do a Gibbs sampler, for example, you know, if you move horizontally, you can see that you're not going to go too far, especially in the tails, okay? But if we could exploit somehow the structure of the target distribution, then probably we could do a better job. So one idea would be to say, well, I'm going to follow the contours, okay? So I refer you back to Mauro's posters on Monday, but in fact, one can make other remarks. Okay, so here is a suggestion of a flow. So I'm not writing the ODE, I'm just writing the flow. And what does the flow look like? So think of this. So this is a function of t. And basically, this is what I could use, okay, in order to propose samples in my HMC, for example. But of course, one can do that in SMC as well. So what I'm going to say here is, okay, so let's define a velocity, okay, which can only take two values, -1 and 1. So it means I can go forward in time or backward in time. And let's say, so x1 of t, you remember that was the horizontal component. And I'm just going to, you know, move at constant velocity, either forward or backward, okay? What happens to the second component? Well, if you take this here to the left-hand side, you see that what I'm saying is define a path such that x2 plus 0.03 blah, blah, is equal to basically your initial point. So what I'm saying here is try to follow the path, okay, in the x2 domain that ensures that the second component that you inject in the normal distribution is constant, right? So basically what I'm doing here is that, of course, I'm reparametrizing because that's a simple example, okay? But you can think of this as a kind of Gibbs sampler when I'm saying try to update x1 independently of the other components, but on the initial Gaussian distribution, right? So I've somehow unbended the banana in this scenario, okay? So that's the main idea. So of course you could say, okay, what's the link with ODEs and what do I do with examples that are less toyish than this? Well, remark that if you replace phi of x with this kind of transformation, okay, and here you've got a fairly general function, small u, nothing to do with a big U, right? Then basically I can try to design a path such that basically this function along the path, right, is going to be constant, right? And you see that what I'm doing is that in a way I'm saying on the Gaussian, just update x1, ignoring the dependence on the, so you're making things independent. And designing this kind of flow, provided that U is differentiable, that's easy. Okay, that's what Hamilton's equations do, right? So we can do this in passing. So I won't stress on this, but basically, so there's another toy example, so Neil's funnel, and you can do the same kind of transformation and go back to these, but this example is even easier, right? Okay, so I won't stress on this. So now I'm going to So here, basically, I was trying to point out the fact that, and actually, if you got example of that contradict what I'm going to say, but I think that these ideas have not been really exploited. You know, the fact that using ODEs, we can maybe define better moves around the space and move away from HMC, right? Okay, so Hamiltonian snippet SMC sampler. So I think it's not very difficult to imagine what it is that we are going to do. So here I'm going to show you an abstraction of the transition from mu(n)-1 to mu(n) in an SMC sampler. And this is what it looks like. So at iteration n-1, we've got our seed particles in blue. And from each of these seed particles, basically, we are growing a snippet, okay, which corresponds to our integrator of some ODE. And then what happens? So in standard HMC methods, okay, basically, then we would look at the endpoint, okay, and we would apply an accept-reject mechanism, right, before a selection, potential selection. But you see that here, what we are going to do is that we are saying that actually any point on the snippet can be used to create the next generation. Okay, so samples that are going to represent mu(n). So you see that this snippet doesn't have any children. Okay, whereas the snippet, which one is it? I think there's a snippet that has two. This one, okay, it's not very visible, but has two children. Okay, so that's basically the main idea of integrator snippets SMC. So here is a nice picture, which is closer to reality. So the target is a normal distribution. We use a normal for the kinetic energy, and we use a leapfrog integrator of Hamilton's equations. We've got 5 particles, and we integrate over a time horizon of 15. So here are the seed particles, and this is the projection in the X space. Okay, so it's a 2-dimensional problem. The velocity does not appear on the picture. And what happens is that from each of these particles, you grow a snippet, right? And actually, by the way, you can see here that HMC is maybe not a good idea, right? Because you see that it's very hard to predict where X is going to land, especially if you just look at the endpoint. Okay? You can see that here we've got examples of snippets. So if you take the green snippet, you know, it starts in an okay region, it goes in a bad region, it goes in a good region, and then it ends up in a bad region. So it's not unlikely that you're going to reject this point if you just look at the endpoint. And here there's a resampling selection mechanism, and you see that the purple snippet gives rise to 2 seed particles, right? And a bit of notation here, you see this is, I may sometimes denote, so this is particle I, so that's the seed particle index, and K is basically your index along the snippet, right? So that's the thing, and this is what the, so there are too many symbols here, but I decided to leave this slide just because I wanted to show you the importance weight. So these are the iterations. So you go across, okay, you visit all the intermediate distributions, and here you see that we index the seed particles, the time, this is the time along the snippets. So we compute all the snippets for all the particles, and for each point on the particle I at time K, basically you compute this importance weight, which looks like this. And here there's a nice interpretation, okay? So this is basically the acceptance ratio of a HMC algorithm. And here this basically takes into account the fact that you're using SMC. You're trying to go from mu(n)-1 to mu(n), right? And then once you've computed all these things, basically you draw from the joint distribution of the I's and K's, if you like. Okay, so over all the n times t plus 1 particles, you're going to, for computational reasons, you're going to whittle down the n times t plus 1 particles down to n again, okay, to create the next generation of seed particles. And there's a bit of regeneration of the velocity going on here. So I'm going to discuss a bit the high-level justification here. I don't have time to go through all the details, but this is the main important point, is that in fact, the algorithm is a standard SMC, right? So in a normal SMC, you would just consider the endpoint, accept, reject in order to get the nice importance weight. Here, the main message is that you can interpret this algorithm as a standard SMC, but that doesn't target from mu. It targets from another distribution, which is this mixture, right? So mu bar is the mixture that corresponds to un, and it is a mixture of this form. So you see, with uniform weights in this case. And so we've got this strange symbol here, and it's very easy to remember what it means. It's the distribution of the transform of this transform of a sample that is distributed according to mu n. Okay, so it's a push forward, if you like. And here, actually, a push backward, if you take into account the minus k, right? Is that right? So I sample from Z, you apply psi minus k to Z, and you obtain a sample from this distribution. And the distribution we're going to sample from is a uniform mixture along the path of the snippet, right? So that's the idea. So that's really the important thing to understand. So what is the interpretation of this thing? So now what I'm going to talk about, and really when you, if you ever read the paper, there are three things to understand, and they're on this slide, okay? So the first thing to understand is very easy, is basically what is mu bar, okay? What is the probabilistic interpretation? Well, if you sample Z from un, you sample K from a uniform, which corresponds to this, then psi n minus K of Z is distributed according to mu bar, okay? It's just a mixture property. That's not very difficult, but that's very useful, okay? And that's the easy part, because of course, the interesting question is how do we go the other way? Because I'm using an SMC sampler that targets mu bar and all the intermediate distributions. How do I go back to my initial problem, mu n? And of course, here we are going to use again sampling this mixture properties. Okay, so the last bullet point is just there if I get questions. Okay, so that's what we are going to sample from. And now I give you a sample from mu bar. How do I construct a sample from mu n? And basically the intuition is the following, is that basically I give you the sample from mu bar n, and I sample k from the conditional distribution. So you see this mu bar k dz is 1 over t plus 1 times this distribution, the push forward. Okay, so trust me, you can define the conditional distribution, and actually you can put your hands on that distribution. You can compute it in many scenarios. Okay, so basically I sample from the marginal of the mixture, and then I complement it with a component labeled by sampling from the conditional. And of course you get this. Okay, so this is correct. What is maybe less clear, but is easy to prove when you've got a piece of paper and you're alone in your office, is that basically once you've got a sample from this, if you apply psi n k to this z, then you get a sample from un. Okay, so how to understand this? Well, remember, what is a sample from this distribution? So I start from the node that is distributed according to mu. So here I drop n for simplicity, right? I create z by applying psi n minus k to z naught. Okay, so indeed I'm distributed according to this distribution now. And now what I do is that I do something silly, is that I apply the inverse, okay, to basically z. So I apply the inverse to this, so I recover z naught, so I'm distributed according to mu, right? Okay, so it's strange. The first time you see it, you think that he's knitting, deknitting, knitting, deknitting, but it turns out to be useful. And why is it useful? Because you can translate this into this. Okay, when you look at integrals, basically what I'm saying is that if I've got a sample from the push forward, right, and I integrate f composed with psi n k, which is this one, right, then basically I've got exactly the integral with respect to mu. Okay, and of course this is valid for any k, right? So I can write this. Okay, my expectation is equal to the average where I vary k, because this was true for all k. You move the 1 over t plus 1 inside in here, right? And you recognize mu bar of the joint. Okay, so now I can use an elementary rule of probability. And of course, what I've got is that the expectation I'm interested in is an expectation with mu bar. Okay, but now I'm weighting basically the sample along the snippet with the conditional distribution of k given z. Right? So that's the thing. So now basically we understand, so it's easy to go from mu n to mu bar. That's easy. It's now sort of clearish that we can go from mu bar to mu, and that this allows us to, once I've got samples from mu bar, to estimate expectations with respect to mu by using all the samples along the snippet. Okay, so that's the, these are the only things to remember. And here, basically, just to say that in standard scenario, this is what the conditional distribution of k given z in a mixture is going to look like. So that's something we can really compute. And this is what the estimator is going to look like. So I've got n particles, and for each particle, I compute my average along each of the snippets, right? So that's the thing. So just a word about the mutation kernel in the SMC. So I don't describe the full SMC here. It's quite gory and not super interesting. But if you use this mutation kernel to target mu bar, basically, you can make this choice. Okay. And this kernel has got a special property, but you recognize the idea that you're sampling along the path according to a specific probability. And here we just refresh the velocity peak typically, okay, but it can be a bit more general. Okay, so there are links with other things in the literature, but I'm going to skip them there. So what are the obvious generalizations to this? So each seed particle, of course, can give rise to multiple Markov chain snippets. You know, it's a bit like SMC, so you can get several snippets that start from the same particle. One thing is that you can use multiple different integrators. You're not restricted to using one type of integrators, right? And in fact, you don't have to use integrators. Okay, everything that I've written has nothing to do with integrators. You just need mappings that are invertible, sort of. And in fact, mathematically, you don't even need that. Okay, but practically, it is enough to have these integrators invertible. You don't even need them in principle to be measure preserving. Okay, you can just introduce a Jacobian in order to take into account the fact that your integrator doesn't leave the dominating measure invariant, but that's a detail. You can also choose weights that are not the uniform weights in your mixture, right? And you can even make them Z dependent if you want. Okay, and that can be interesting because this is so something which we haven't fully exploited yet, but you can use this as a variance reduction technique because you can optimize the weights to minimize the variance of an estimator. Okay, so that's described in the technical report, but we haven't really fully tested the idea. And again, crucially, the mixture representation is quite nice because somehow, so it's not the algorithm, but it contains the algorithm in some ways. And what is nice is that basically you can use different integrators, right? So that's quite interesting, and we've started to exploit this in various scenarios. So all these symbols and everything, so does it actually work? So it seems to be, so it's only very recently that we started to really understand what's going on and what to show to convince first ourselves that it's worth it, and then hopefully others. But there are various things. So first, we achieved the full recycling of the snippets. Okay, so that was so we tick that box. The other thing is that because we've managed to reframe everything into the standard SMC framework, then we can use actually recycle all the SMC results. So for example, everything that you know about estimating, normalizing, control, it works in this case. Just recycle existing results. One thing that we found interesting is that, in a way, contrary to how you would implement a waste-free algorithm, standard waste-free algorithm or others, basically here competition is really across all particles that you've generated. Okay, if you were to use an HMC several iterations for one particle, you see that the particles would interact with themselves along basically one integrator, whereas here the competition is more global, and it seems that it is healthy, but we don't understand that mathematically. Okay. Not important. Okay, so what we've observed is that, and I'll show you some pictures, is that this strategy seems to be quite robust to bad choices of epsilon and t. So we all know that in HMC in particular, using epsilon and t is crucial to get good performance. And here what we've observed is really robustness. Okay. And there are many other properties. So for example, for HMC, it is known that averaging is a good idea, especially when your coordinates live on different scales. And basically, this is part of the algorithm here. It's not an additional stage or doesn't cost you more. And another thing, I'll show you some pictures that are, I think, very interesting, but preliminary, is that basically because of the SMC, we've got all those particles and we can compute many statistics about the integrators. Okay? So there is the hope that you can design adaptive SMC algorithm in a quite well-informed way because of the population, right? So other things that are in the technical part, so I'm just highlighting things in passing, but they are more detailed in the report, is that in fact, for a long time, I was a bit wondering about what the benefits could be of this thing, because you're not adding noise and somehow no additional ergodicity, whatever that means, okay, because everything is deterministic. And in a way, what you can show is that the psyches act as potential as control variates, that's for sure, but they can be bad control variates. Okay, they can introduce positive dependence. Okay, so that's why introducing those weights, okay, learning good weights is a possible strategy. But I don't think this is the main advantage of the algorithm. We've also investigated actually the notion of optimal psi. Okay, so if I give you a problem, integrate this with a particular function. So we haven't fully tested this, so that's still work to do. And another interpretation is that basically we are sort of performing a kind of Riemannian integration along the integrator orbit, right? So that's promises to reduce a bit variability. Okay, so there are links to other things which are given here, and including actually the Raptor again, who worked on his windows of states, and basically it's exactly the same idea, but in hidden, but in the context of Metropolis Hastings algorithm. And there's a link also with what is it called? Multinomial HMC, which is itself derived from Radford-Niels ideas. Okay, but I won't get into these ideas at all. This was meant to take me way away from all this. Okay. How much time have I got left?
Maybe 5 minutes, including questions.
Okay, so I'll show you a couple of pictures, which are basically some of the pictures that Mauro showed yesterday. So here, I'm going to, let's assume we are interested in sampling approximately from a manifold. Okay, so basically I've got, in this case, we consider the normal distribution, but we are going to constrain it to live around basically a manifold, which is another Gaussian. Okay, so basically I'm just constraining the support of the Gaussian to live on another ellipse, or at least very close to an ellipse. And we are going to use two integrators, so thug and snug. So thug is good at following contours, and thug is good at basically jumping across contours. And I don't provide any details about how this works here. So here are various parameters of the algorithm. And here is an illustration of the, so it was very hard to show the robustness, but here we've got some ideas. So what are these plots? So each plot corresponds for the problem to the scatter plot of x1 and x2. So the first two coordinates of the algorithm. Here we've got t, the length of the integrator snippet, so 10, 30, and 50. And in these directions, you've got to think of the plot in the columns in groups of threes. Okay, so this corresponds to an epsilon. So the snippet, the parameter, the step size of the discretization of DOD, we are considering to follow contours and move across contours. So that's for epsilon large, middle value, I can't remember the values, and a small value of epsilon. So here the integrator is very good. And so that's for the groups of threes. And we consider for each group, we've got three algorithms. So we've got, this is our algorithm, the algorithm that only uses the endpoint of the snippet. Okay, and that's basically a more traditional SMC algorithm that would use a Metropolis Hastings algorithm, which actually two of them, and it's a mixture of the snug and thug. And what you observe here is that indeed increasing T can be useful, but you see also that even when epsilon is very bad, basically we still do a much better job than the other algorithms. Okay, and if you think of the trajectories that I showed you earlier, of course, many of the endpoints are going to be bad by design. Okay, whereas here we cover them. Okay, and I will skip this in the interest of time, although it's nice. So that's basically statistics over all the particles that can allow you to adjust the various parameters of the integrator. And that's it. Thank you.